I'm Chi, a first-year PhD student at Edinburgh Napier University, and I would like to give a short talk about our position paper that used genetic algorithms to automatically select compiler flag and library version to minimize execution time. Selecting compiler flag manually is considered as a complex and time-consuming task due to the large number of possible combinations. There are optimization levels such as 01, 2, and 3. They are preset combination of compiler flag, but they does not always help to optimal performance. There are tools that tune compiler flags, and they are proved to be better than optimization levels, but they mainly optimize flags without configurable values. Optimizing flags with configurable values is not entirely new, but it's relatively underexplored compared to non-configurable flags. And also, link and directory flags can be used for selecting different library versions, but they are also underexplored. So our aim is to create an algorithm that select all of these flags together. So here's the workflow of the proposed algorithm. As you can see, it's divided as 3 stages. We can consider each stage as a separate genetic algorithm. All the genotypes in each stage is a binary string, and the phenotype is the command to run the configuration script. The fitness function will returns the average execution time across 1 or 0 if we encounter any execution or compilation error. We'll dive into each stage separately. So in the first stage, the genotype is a binary string where each bit indicates whether a flag is enabled, and we are just changing the highlight part in the phenotype. And once this stage ends, we pass the most effective flag, non-configurable flags to the next stage. So in the second stage, we still use 1 bit to indicate whether a flag is enabled, but we need additional bits to encode its values based on some value ranges. And the phenotype, we'll use the most effective non-configurable flag from the previous stage. The only thing that changed is the configurable flags. And once this stage ends, pass the most effective non-configurable flag from first stage and configurable flags from second stage to the last stage. And in the third stage, the genotype basically encode the library versions, and we need a special genotype to phenotype mapping that creates link and directory flags that point to the specific library versions, some directories of this specific library versions. And once this stage ends, we just got the most effective optimization flags and library versions. So there are a few potential benefits compared to a single stage algorithm. This 3-stage algorithms reduce the search space. Also, as we are only changing 1 type of flag in each stage, it's easier to identify whether a compilation or execution error is related to which type of flag. We expect that once the first stage ends, we can already get a configuration that is better than optimization levels, as most research papers prove that. And so the computational cost for second and first stage should be reduced. Before we execute the GA, we need to conduct two pre-processing tasks. The first one is to collect the optimization flag from compiler manual or from the help command. And we need to filter some non-configurable flags that cause errors. And the second task is to compile all the library versions. We need a unique directory name, as you can see for each library versions, as you can see from the dependency graphs. Even the dependent library itself can have its own dependencies. So we need a unique name to reflect these dependencies. And each directory will contain subdirectory, including lib, include, and bin directory for library selection. And they are compiled and linked statically to ensure the correct version is selected. There are a few edge cases when we consider configurable flag. First, say if we need to encode 6 distinct values, we need at least 3 bits, but 3 bits can store up to 8 values. So we handle this genotype to phenotype type mapping by wrapping around. The second edge case is that some flags, the value range of some flag may range from 0 and theoretically infinity. So we replace infinity with a finite positive number. And the third edge case is that some flag may have the same name, but they can take different number of configurable values. We allow them to be all enabled encoded in the genotype, but in the phenotype, we only specify the one with more number of configurable values. By default, GCC will only the rightmost flag will be enabled in GCC if you enable all of them, but we want to control this behavior by ourselves. We did some preliminary experiment for this selection, and it's not included in the paper due to page limit, and it's quite explanatory. We developed 3 different versions of GA. GA1 select only non-configurable flag, and GA2 additionally select configurable flags, and GA3 also select library versions. Noted that we use quite a small population size and a small number of generations due to resource constraints, as we test it on a scientific application where compilation may take at least 5 minutes or can take an hour, depending on which flags we are using. We replace infinity with 15 for any flag that accept value ranges from 0 to infinity. Our test program is RxCM, a regional climate model written in Fortran and C. So we need both Fortran and C compilers. It depends on multiple libraries, making it a good fit to test library version selection. And it also depends on some input parameters. The search space for GA1 is around 400. And when we consider GCC optimization flag non-configurable, when we consider 19 more GCC configurable flags and 8 G4chan configurable flags, it's increased to around 600 bits. And regarding the benchmarking process, we basically compare 6 configurations. And for each configuration, we compile it with, we repeat the compilation. We compile RegCM and we repeat the compilation execution for 10 times on 32 processes. The one time when we consider configurable flags and library versions, it's much longer than only considering non-configurable flags. And regarding the runtime for our target programs, our one-stage GA that optimize all types of flags result in the optimal performance. It's interestingly, GA2 result in performance that worse than GA1. And we are interested in why what factors result in such performance. We keep all the configurable and non-configurable flags generated from GA3, but we change different library versions, and there are no big result improvement. So we conclude that the reasons for improvement in GA3 are mainly based on optimization facts instead of library versions. So in this experiment, we didn't prove that selecting different library versions can improve execution time. There are a few challenges and future work I want to mention. We use a unified number to replace infinity, but I think it should be changed dynamically, and it should be flag specific. And the second challenge is to ensure flag reliability. In our initial exploration, we find that even if we use the same flag for compilation and execution, sometimes it succeeds and sometimes it fails. So and for future work, our first and foremost work is to benchmark the genetic algorithms for more applications and perhaps more problem instances, and perform hyperparameter tunings for GA hyperparameters. And we would also like to test it with alternative optimization objectives like code design and energy consumption, etc. We would also like to consider using variable length genotype or specialized genotype to phenotype mappings to ignore those flags that result in compilation or execution error or performance decline. We could also consider selecting more additional factors such as command line interface options, pre-processing directives, and environment variables. That's the end of my presentation. Thanks for listening.
Yes, thank you very much for the intro, for the presentation. And then, so let's now move on to the Q&A one. So let's start off with from the online. Let's see, what do we have? Let's see online. No. Oh, what about from the chat? So we don't seem to be the case. We don't have the question from online. Is there anyone from offline, from on-site who would like to ask a question? Anyone would like to start off first? We'll try and use this like fast, you know.
So hopefully you can hear me, Chahong. It's Bill Langdon. What I wanted to ask was, you know, there will be a special issue of the ASE journal looking at extensions of the work presented here. And so I was wondering, do you feel that there will be a lot of, it would be easier and straightforward to apply your GA to other compilers, maybe to other languages?
I think I have to change it manually to adapt the program, the genetic algorithms to benchmark other programs or in the same language or other languages. So I think it's not quite straightforward.
So is that something that you would like to do, or is that something that is really outside the scope of the existing work?
It's mainly variable length genotype and maybe specialized genotype to phenotype mapping.
Okay, thank you.
Right. So is there any more question from online and from on-site? Okay, so if not, then we just take one last question, which from me. So I would like to ask Michelle, like what do you think would be like the first group of people who is going to like be interested in this, and what would you say to be like the most critical part if someone were to pursue your work further? What would be the first thing that you think that like they should probably do about this one to further extend your work?
I think they have to plan the experiment and resource carefully, because I tested on a scientific application which consumed so much resource, and I didn't really plan it properly, so I only tested on one problem instances based on my limited resource constraint.
What was the program that you test your like current prototype with? What was the program?
It's called Wexium.
Oh, I have no heard of that one. On this slide.